Welcome, everyone. We're going to get started in just a minute. We're going to let everyone take a second to get into the Zoom link. Thanks again, everyone, for joining. We're just going to give it one more minute. We have a lot to cover today, but want to make sure everyone's able to get into the Zoom before we get started. All right, I think we're going to kick things off. Welcome, everyone. My name is Katie Kaluzny. I'm the Associate Director at the Illinois Green Alliance. We're so excited to be hosting this session today, the heat pumpification of buildings. In fact, this is our largest registered for webinar yet. So definitely a popular topic. We're excited you're all here and tuned in. Really want to thank our programs committee volunteers for putting this together. And really they put all this content together and pulled all the speakers together for you all. So I'm going to turn it over to Mohammed from our programs committee to kick things off, tell you a little bit more about Illinois Green and what you're in store for today. So Mohammed, take it away. Thank you.
Thanks, Katie. Hello, everyone, and welcome to today's webinar, Heat Pumpification of Buildings, Lesson Learned and Practical Consideration. My name is Mohammed Haidarinejad, and I'm an assistant professor in the Department of Civil, Architectural, and Environmental Engineering at Illinois Institute of Technology. I am the co-director of the Built Environment Research Group at Illinois Tech, where I lead research and teaching in the areas of building, energy, and environmental systems and indoor air quality. Today's program was put on by the Programs Committee, an Illinois Green volunteer group that coordinates educational events covering a wide range of topics. The team that put on today's event consists of myself, Mohammed Haidarinejad, who led planning of the program, Alan DeSalt, Jason Leflore, and Dan Mooring. You all have been muted upon entry, so please type any questions you have into the Q&A, and we will get them answers at the end. This webinar is being recorded and will be sent out in a follow-up email. Next slide, please. Illinois Green Alliance is a membership-driven nonprofit organization that advances green buildings and sustainable communities for all. Our 5-year strategic plan pushes the green building industry to meet or get on the path to net zero. We achieve this work through educational events, such as panels and building tours, by engaging communities and partnering with organizations across Illinois, and by advocating for new policies and legislation. Members can view our recorded webinars on our on-demand webinar library. Learn more about membership, see upcoming events, and get involved by visiting our new website, illinoisgreenalliance.org. Next slide, please. I want to take a moment to recognize Illinois Green Alliance's sustaining sponsors who make our work possible. A special thank you to our gold level sponsors, ComEd, Resource Innovation, and Sloan. Make a commitment to advancing green buildings and community across the state. To start a conversation about sponsor partnership today, illinoisgreenalliance.org/sponsorship. Next. We have a great lineup of speakers for today's program. So let me first introduce our moderator to kick things off. She will introduce each speaker in the order of their presentations. We will have ample time for Q&A after the presentations conclude. Jackie Montestioca is the Director of Building Electrification at Elevate. Jackie is responsible for managing equitable building electrification strategies, including developing and implementing retrofit projects in coordination with technical teams across the organization. Prior to her current role, Jackie worked on Elevate's National Strategic Engagement Team, specializing in technical assistance, project management, and residential program design and implementation, serving both subsidized and naturally occurring affordable housing. She has managed a variety of projects, grants, and staff working on energy efficiency and resiliency across multiple states. Jackie?
Thanks, Mohammed. Hi, everyone. I'm excited to be here and just wanted to give a brief introduction to Elevate in case people hadn't heard of us before. So Elevate is a nonprofit organization that works nationally and is headquartered here in Chicago, which is where I am. We work to seek just and equitable world in which everyone has clean and affordable heat, power, and water in their homes and communities, no matter who they are or where they live. And our program's policy, agenda, and partners reflect this commitment. Next slide. So we're here today to talk about heat pumps, but it's an exciting piece of a larger conversation. So we know heat pump technology is being featured in a lot of pilot programs, incentivized at federal and state levels, particularly in Illinois' affordable housing sector. And that it's just a really big piece of single family and large multifamily decarbonization efforts. Previous sessions hosted by Illinois Green Alliance, such as the Heat Pump-a-Palooza session, have focused on the technical and performance components of heat pumps. And we know there's a lot more to the real world implementation. So how do key decision makers in a project evaluate the costs, benefits, and implications of using heat pumps? What are the experiences of those implementing heat pumps, especially in cold climates? What lessons have been learned from owners and contractors and occupants that have undergone retrofits for these space heating systems? What are the design decisions, the installation barriers? We're excited to gather around these types of questions today and pull together a panel that includes perspectives of homeowners, developers, designers, contractors to evaluate applications in the single family and multifamily space. A few things I want to pull out before I pass it on to Nate is just some themes to lift up around the presentations. Well, one or two things to clarify that we are talking about cold climates. So Northeast, Midwest projects are featured. We know the technology is advanced. We're not questioning if it works, but how. We're talking about air source heat pumps. And this session is interdisciplinary. So this is not a session just for contractors or just for engineers. We're here to put the pieces all together and learn how we're working across stakeholders. We want to keep in mind equity. So electrification doesn't always mean energy efficiency or energy savings. And it's important to put people at the center of this and understand how we implement and design and be mindful of energy burden. This could also apply to equity in the workforce, as well as how we're distributing funding and incentives to cover implementation. Finally, I'll say it's important to remember to meet people where they are. We know that heat pump technology is a step in the right direction, but we have to design in stages to meet people where they're at and remember people's experiences first when talking about the technology. So we're kicking it off. Nate's next here, and I just want to read his bio and introduce him. Worked with Nate through his work at POA before. Excited to discuss this very exciting topic today. So Nate Dick has been POA's Director of Energy and Capital Projects since 2019, serves on POA's Design and Building Performance Team, which is responsible for discrete energy projects, design and construction standards, development project design support, preventative maintenance stewardship, and information technology strategies to improve portfolio oversight. Nate does a lot. In this role, he helped POA to achieve its Big Reach and DOE Better Buildings Challenge, a national effort of 345 organizations to improve energy intensity across their entire building portfolio by at least 20% within a decade. Prior to joining POA, he oversaw a new construction energy efficiency program for residential and multifamily buildings for Eversource, the largest electric and gas utility in New England, and also worked on the implementation side of residential energy efficiency programs for Conservation Services Group. He's a certified passive house consultant and certified energy manager. Take it away, Nate.
Thanks, Jackie. That really makes me sound a lot more interesting than I probably am, but thanks everyone for joining, and excited to talk to you all about heat pumps and POA's experience with heat pumps in our portfolio. So just as a quick quick info on POA as an organization. POA stands for Preservation of Affordable Housing. We're a national nonprofit developer, owner, operator of over 12,000 affordable housing units in 11 states and the District of Columbia. And we are definitely fortunate enough to have a dedicated design and building performance team, of which I'm a member of. So we consider ourselves very blessed in the affordable housing community to be able to dig into these interesting problems and help people have better homes to come home to and work in and grow old in. So we've been advancing electrification for a number of years, and I want to discuss some of the reasons why we do it and what opportunities we have further on that effort, which lends itself to this conversation, specifically in the rehab setting. So as you can see, some of the big reasons, which I think we all know, and what we believe is that the future of the electric grid is going to be cleaner domestically. There are obvious carbon reduction benefits with going to electric. The improved source energy efficiency of electrifying systems to high efficiency air source heat pumps is obviously a good way to utilize the finite resources we have. And then the final two, I would say this gives us some opportunities to sort of diversify our supply and cost curtailment options for our own portfolio. And lastly, we want to lead. We want to be sort of at the forefront of this. So those are some of the reasons why we do it. And I'll try to go through these as quick as I can. Hopefully folks can see this slide clearly, but basically this is just showing the levelized cost of electricity by different types of electric generation. And this is from the Energy Information Administration. And you can see in 2023, that green line on the left graph is basically the average cost of gas generation, rather electric produced through gas-fired combined cycle plants, while that yellow line is your solar cost per megawatt hour. So in 2023, those are pretty close, but as you move to 2026 and 2040, you can see that solar cost is much lower. So we think there's going to be a lot more clean energy coming online in the future, and I think folks can agree on that. So carbon reductions with electrifying. So this is a graph from the International Panel on Climate Change Working Group, and you can see the life cycle emissions from a gas combined cycle power plant. And if you look at that middle number, which is 490, I think that's essentially grams of, or tons of CO2 equivalent per kilowatt hour produced. It's pretty high in comparison to a lot of these clean sources. So as the grid gets cleaner, we're also going to be reducing our carbon. This is an interesting graph that I thought was really helpful in understanding sort of the source energy efficiency of air source heat pumps in comparison to typical gas-fired equipment at a site. So this graph basically shows in different regions of the country, if your energy is produced with clean renewable sources and really efficient gas combined cycle power plants, as represented by the purple bar, you will see that electric heat pumps in cold climate, electric heat pumps are obviously much more efficient than any gas-fired equipment that you can find. And as your grid gets, less efficient and it goes to maybe a coal or steam generation to produce the electricity, which is represented by that blue bar, you're going to see that the source energy efficiency is really not as ideal in comparison to a gas furnace. So what this is basically saying is, as the grid is cleaning and we're sort of getting rid of these old coal steam generation assets, the source energy efficiency of heat pumps is obviously a lot better. So those are the reasons we do it. And we do this for our residents, for our staff, for our environment, and this is something we believe in. So there's obviously a diversity of supply and cost curtailment options with electrifying. We can build our own solar. We can take advantage of virtual net metering or community solar credits. In some cases, these credits we can get discounted at 10, 20, 50%, which is not nothing when you scale it. So we have a way to sort of control those costs and do it with clean energy sources. And in addition, we could build our own solar, so that could help with our electric costs and drive those down. We have more control of that. And then lastly, batteries are becoming more viable in terms of helping us shave off those peak demand periods. And there's some cool programs out there. One is in Massachusetts, actually through Eversource, who I used to work for, called Connected Solutions, which basically gives owners of these battery assets an income stream to help shave their demand and help the grid overall. So, and finally, we want to lead. I think having been here for 3 years, it's pretty obvious that that our organization is focused on testing out solutions, trying things out, and figuring out what works so that we can improve the health of our planet, improve the health of our communities, and help our residents. So I thought this quote was very applicable, because sometimes I wonder how it's all gonna work out, but you just have to remind yourself, we just have to keep moving forward, trying things out. And it's not easy. It's not easy work, and I'm sure Alex will be able to attest to that. With retrofitting some older buildings with newer high efficiency equipment. Same with Jason, but just believe in it and test things out. And there's a lot of good resources out there to help figure out this problem. So most of our work that we've done has been in the new construction setting. And this is just an image of a VRF system that we have in the Cape. I say the Cape Cod in Massachusetts. And these systems were installed, I think, over a year ago. So most of the equipment that we have in our portfolio is basically in our new construction sites. And moving forward, there's a strong emphasis on electrifying all the heating and cooling, and ultimately hot water as well, so that we have a full electric building for all the reasons that I outlined. In some cases, we have one-to-one systems that are installed. I think that's in Boston, that image that just popped up on the top right. And this is just a shot of sort of the central controller that we can utilize to manage the large central systems to help control space temperatures, look at trending data, figuring out how the system is satisfying temperatures when it's running, how much energy it's using. And I'll talk a little bit more about that. But currently in our portfolio of about 12,000 units, you can see there's about 1,200 that have heat pumps. Another 11,000 roughly are predominantly gas-fired hydronic heating systems. So, this blue slice is pretty representative of new construction, although there's been maybe 600 or so units that were rehabbed from existing electric heat to high efficiency air source heat pumps. So we have a pretty good data set on sites that have this from varying ages and building types. But moving into the future, we're going to be expanding this footprint of air source heat pump technology and even a little bit of water source, which I know we're not talking about a lot today. But like I said, all of our new buildings are going to incorporate air source heat pump technology. So it becomes more of about a quarter of our total portfolio that will have this type of equipment. So just a few more images. These are wall mounted terminal units. Those sites were in Boston and the Cape. This is a site in Chicago that Alex is familiar with. This is a ducted fan coil in a unit that we actually, if I had to choose, I would want to put one of these in all our sites, but obviously there's space limitations and cost considerations if you're doing that in an occupied space. So it's not always possible. So a few lessons learned. You can see in this image, refrigerant line insulation is not properly installed. There's moisture getting inside that insulation. That can be a real big problem for all these line sets that got run. And of course, that insulation, if it's not UV protected or have the proper moisture protection, it can evaporate pretty quick, decreasing your overall efficiency. So got to pay attention to that. Don't skimp on that. Same thing with this next image. This was from a roof in Chicago, where this was pretty evident that we didn't get the product we had hoped for. The other thing that we've run into at some sites is the condensate hose on this terminal unit in the living room is obviously kinked. So that condensate not being able to drain properly, that can cause a lot of problems. So proper installation is critical, especially on those condensate lines. No kinks. You don't want to see that. So I think, other lessons learned going back to sort of the single terminal unit or a one-to-one unit is sometimes those systems, if they're a one-to-one or a single outdoor unit to two terminal units on the inside, they have a minimum compressor capacity. So depending on how much sensible loads you have or how much insulation your building has, you may be able to satisfy your temperatures very quick. And that leaves very little space for humidity to get removed from the building. So it's very important when you're designing these to consider the sensible loads and the latent loads in those spaces, and ensure that you are not running a minimum compressor capacity that's going to cool that space too quick and not remove the humidity. And in coastal environments or high humidity environments, you need to be very conscious of making sure that you have proper dehumidification in place. On reporting and data, I would say our experience has been not to link up the VRF master controller with a laptop. There's a lot of options out there that now you can go direct into the control and get remote access without the use of a laptop. And some of our original sites, we needed that laptop to house the data. And due to Windows upgrades and other upgrades that need to take place for security, that laptop loses the data during those shutdowns. And that's really not fun if you're trying to analyze things at a deeper level. I show these units because this was an example of a site that had existing electric baseboard and through wall window AC. So this is I think a good place for folks to start if you're thinking about retrofitting existing buildings. Find those buildings that have the existing electric resistance or through wall AC equipment. They'll probably have the proper capacity and energy that you'll need, and you won't have a lot of those large infrastructure costs to deal with. So this is just to reiterate some of the recommendations. start with sites that have electric heating and cooling. That's not air source heat pump. I think in some of our recent rehab work too, I think there's still some naysayers out there about the ability to heat at colder temperatures. So, there are products that offer gas options, not that, we want to go back to relying on fossil fuel, but if you had to gain that efficiency and that additional carbon benefit and get a little bit of gas for the peak hours of heating, that's a potential way to overcome that hurdle. If you're installing large VRF equipment, be very conscious to look at the demand cost implications of installing those, because your rate class is going to likely change, as well as the service that's going to need to be going into that building. And then this one actually just recently came up again on the bottom with a site that has VRF equipment, but has a large resource space for community gatherings and community trainings. That space only operates in heating or cooling mode. So when there's a huge gathering in the wintertime, there's tons of latent loads that need to be addressed, and there's a lot of heat in that room. And since the system can only be on one or the other, I think it's good for designers to consider that heat recovery option in those zones. So I'll sort of breeze through this because I'm running out of time. But if you're wanting to limit refrigerant, there's obviously a lot of housing out there that has 2-pipe fan coils, and what you can do is consider an air to water heat pump. But I know we're not talking about that specifically, but that's another way you can electrify your heating and cooling without doing, I guess, a ton of refrigerant around the building. So something to keep in the back pocket, or sort of ace up your sleeve in order to electrify. And then this is an example of a site in Chicago that I want to touch on. So this was an existing gas steam building, limited insulation, that we were exploring with Elevate to upgrade to air source heat pump technology. So there's the old steam boiler. They had gas cooking. The panels were pretty limited, maybe 100 amps, through wall window ACs. We got a heat balance calculation done, A3 and F3 not satisfying the heating demands that would be needed for these spaces. So a little bit worrisome. So these are the types of things that you're going to run into when you're thinking about retrofitting existing buildings, especially old housing stock in Chicago. But there's a list of considerations that you have to have when you're thinking about that, which I won't go into all the details on, because I want to get to some of the meatier stuff, which is the cost. So this is a building that we paid the heating and residents paid the cooling. So this is basically the pre-rehab costs for our common areas, and then the post-rehab estimated cost based on the analysis. And then the same for average tenant energy costs. So going from us paying the heating to them paying the heating. And again, this is an affordable site, so we don't want to do that. Overall, the building costs increased slightly. So how do we address this? So these are the challenges that we're facing. We're lucky enough to have the first cost likely covered, but in terms of operation and how we share these costs with residents, it's very tricky. Once I updated the gas rates, because the gas prices have increased, as we all know, this looks a little bit more favorable in terms of the overall energy cost savings, but still those tenants are burdened with $300 more than they had prior. So how do we address that? Well, like I said, there's community solar credits that we can tap into that help drive down our electric costs for our residents or for our house meters. At 20%, you get about $1,300 per tenant. Now, if you get a better deal, you can get that number down even more, down to about $1,000. So it's almost cost neutral to upgrade. Of course, the site energy goes down quite a bit. So, I'm sort of running out of time here, but, we have to weigh the first cost of this job, this is breaking down to about $38,000. It needed some additional insulation work, some new equipment. Upgrading to air source heat pump is pretty expensive. Now, if we upgraded our steam system, which is aging, what's that cost going to be? So I assumed, I don't have a firm price on this, but I assumed it was about $75,000, maybe more. Alex might be able to tell us. But the incremental cost in this case is only, $7 grand now to go to the air source heat pump. Now, if we weren't adding the cooling, the ducted cooling, the first cost or the incremental cost is obviously a lot more to overcome. So what's going to change is our gas prices going to go up? Are there going to be bigger sticks out there from the city of Chicago for us to do more to save energy, to reduce carbon? What are the other things that are going to change for us to make this pencil? So those are just a couple things, but I'm welcoming questions in the Q&A session to talk about this. And sorry I had to rush here at the end, but obviously a lot to talk about. So thank you, and I'll pass it back to Jackie.
Thanks, Nate, and thanks for covering some of those really important questions at the end about how those costs will shift. And there are questions from the audience that we'll put a pin in and ask later. Let me, for now, introduce Jason so that we can hear from his perspective as a homeowner. Jason Leflore is a senior manager at GTI Energy and focuses on emerging technology deployment and scaling building envelope retrofits. Currently, he's involved in applied research initiatives, including demonstrating technologies for the Department of Defense, Department of Energy, and NYSERDA, and is a voting member of the ASHRAE 227 design standard for passive buildings. He joined GTI 10 years after founding a successful energy consulting firm, EcoAchievers, where he worked on many net zero energy projects, instructing best practices and testing building performance. An unapologetic early adopter, Jason drives an EV and lives in what might be the only home in North America to have had both a thermally driven gas heat pump as well as an electric cold climate air source heat pump. Go ahead, Jason.
Great. Thank you for that introduction, Jackie. And yeah, I do a little under the weather. Sorry, but I'll do my best here. I work for GTI Energy, hiring many positions if anyone's interested, but I'm going to put on my homeowner cap today and talk about personal experiences that I've had with 3 different heat pump systems. So going back almost 10 years ago to a house I lived in Oak Park. This was built in 1912 and was actually on the Greenbelt Home Tour back in 2015 for those of you that went in-person events back before there was a pandemic. We in this house, the front porch was an unconditioned porch that we converted to a conditioned space. It actually became my own office, my work office. And in order to do that, we needed a space heating and cooling solution because there wasn't ductwork from our furnace running out all the way out this far. So for this, we ended up going with a Mitsubishi ductless mini split heat pump, which you can kind of see in the image there on the with the arrow pointing to it. And one of the things that's worth noting is that at this time, the Mitsubishi systems, they didn't have the Hyperheat product line that's now available for cold climates. And what you can notice in the spec sheet for this model that I installed was the heating ability at 47 degrees was 13,600 BTUs. And that basically got cut in half when the temperature gets down to 17 degrees. So those are the common rating points that most of these mini splits, or any heat pump, I should say, are rated at. You want to know what the capacity is and what the power consumption is at those different temperatures. So anyway, we got this installed and I did adjust the dollars. I found the original quote, an invoice from the contractor in my email, and inflation adjusted the cost there for everyone's benefit. A couple lessons learned, like Nate mentioned, there is some condensate issues. I wasn't expecting that to happen in the wintertime, particularly condensate coming from the heat pump unit. And I didn't run this unit all the time. I was running it if I was out there and turned it off sometimes. So the line can freeze if there's not proper drainage in there in that condensate line. And that prevents operation if there's no way for condensate to go down and drain. So the other big lesson learned here was do a load calculation. Your HVAC installer should be able to do this. Don't just base it on the square footage of the space, but really take into account everything like a large number of windows that you might have in a space you're trying to serve. So knowing the spec sheet a little bit and seeing that there would be capacity drop off, when I had this installed, I directed the installers to put the outdoor part of the heat pump underneath the porch in a sort of buffer space, thinking that, oh, well, this will help, give it a little bit more warmth and it won't have to work as hard in the wintertime. And so you can see the line set running around the outside the house, and it punches through to that below the porch floor crawl space area. And the lesson learned here is that it was a dumb thing to do, quite frankly. The buffer space, it didn't help that much in winter, and even worse, it put a lot of heat in that crawl space underneath the porch during summertime when it was cooling, making it overheat. I actually had to open up that little access hatch in order to get heat out of the floor. So, lessons learned. I see people doing this on commercial jobs sometimes still for spaces. So it's worth noting and learning from that. We just should get equipment that works right. So fast forward a few years, and we moved from Oak Park to Geneva and bought a house that was built in the 1960s and had a major sunroom addition in 1985. And that's what all this, that glass photo on the right, you can see. And this is a room that has 3 walls of windows and 1 ceiling of windows. Double pane glass, a couple of replacement panels have low E coatings, but for the most part, it's a hot box. And you could see a log temperature here when I wasn't running the heat pump for about a year, and just the temperature swings that this one room gets is just very remarkable, from 20 degrees up to 120 degrees. Sometimes half of that in one day. So the important thing to do, lesson learned from the first time, right? Do a load calculation. So I did that on the whole house, one space of which was the sunroom, and which I'm highlighting here as, so the heating needs for the space was around 12,000 BTUs estimated, and then cooling was about half that at 6,500. So great. With that, I was able to make an informed choice about the heat pump to choose. And Mitsubishi now had to introduce their Hyperheat product line, which basically allows for full capacity down at lower temperatures. We placed this unit on the north wall of the house, so it was kind of in the shade to maybe help with the cooling side in the summertime. Here's the spec sheet. So you can see it gets 20,000 BTUs at 5 degrees, new rating point that they optionally added to their spec sheet at 5 degrees in addition to the 47 and 17. So that just helps understand how the system works. The one thing that they didn't have listed there, the power consumption at the lower temperatures. So that's something, I wasn't really clear on at the time. So we put this system in 2015, and you can see the adjusted install costs there. And just to better illustrate, here's a chart from Mitsubishi showing that as a function of outdoor air temperature on the bottom, your standard heat pump in the gray sort of dropping off on capacity. The amount of heat that it can put out isn't as high at lower temperatures, but a heat pump that's a cold climate rated heat pump like this Hyperheat system was able to maintain 100% until about 7 degrees or so. That's when it looks like it, on the chart, it starts to drop off after that point. And so the question was, how does it work on a really, really cold day? I put in some instrumentation to monitor the power consumption of the unit, as well as monitor the temperature of the sunroom itself, as well as outdoor. We can get from weather data from an airport nearby. And the little blue dots you're seeing are the power consumption. And what was interesting here is to see that, there's sort of a base load power consumption, but when that compressor cycles on and off, sometimes there are some peak draws that spike basically. And for me, that was interesting because down the road, if I'm thinking of battery storage or in resilient solutions, you need to know what amount of peak draw you might have at a given point in time to ensure that you have the capacitor in the building to manage a load, right? So anyway, very cool day actually this year. The high was 12, the low was 3. You could see there was still some challenges for the heat pump, even though it was running, to keep the space warm. And I think it was mainly because the infiltration, when we did the load calculation, I did infiltration on the whole building. Should have done it just for the sunroom itself, because I think there was a lot more infiltration between how they assembled those glass panels. And so we were getting a lot more load than we should have. So I should have probably oversized it even more. I've always been a big fan of right sizing HVAC and still am a big fan of that. But knowing that you have a variable speed system like many of these heat pumps, it can ramp up and down and meet part load conditions, but give yourself that extra headroom that you might need for peaks. I mentioned the battery consideration if you're going to be sizing something to serve the space heating and conditioning needs of a home. So some lessons learned. For those of you familiar with Drawdown, very nice book by Paul Hawken. There's a list of the impactful solutions to impact global warming. The number one solution is refrigerant management. And we have a lot of short-lived climate pollutants in traditional refrigerants. And that's particularly true for R410A, which is what's typically used in many of these residential systems. My heat pump on the sunroom, I've had to have it charged 3 times because of leakage from the refrigerants. And so there's actually some research that ASHRAE has done on this to see what types of refrigerant leakage fittings might leak more than others. And the flare type fittings, which are often manufacturer recommended, are particularly challenging. So that's what was originally done. The first 2 times I had or it wasn't addressed for the first 2 times I had it recharged. Third time I had the contractor braze the fittings, solder them basically. And so a lesson learned here for others is to specify press fittings or brazed fittings to have a much more decreased likelihood of failure on the refrigerant lines in the future. I mean, you can also leak test them too, but I'm not sure how that works over time as well as some of these other systems. So I'm interested in heat pumpifying my entire house. I talked about the sunroom itself. And when I was getting a charger installed for my EV, I had an electrician quote upgrading my old panel, which is a 100 amp panel, to a 200 amp panel to be able to accommodate an additional heat pump. And also got a quote from an HVAC. So it was sort of ballparky. So they gave me a range low to high. And I sort of gridded it out here on what that impact was. So my questions were, wondering like, well, what, I understand the financial side of this. What's the implications from an energy and carbon basis? So I actually did an energy model on my home using a condensing furnace that I have in there now versus would have to go with a VRF from Mitsubishi, sort of like just because of the capacity needs for the house. Without improving the building envelope, it would have to be a bigger heat pump. And that has some impact on operating expenses for the system over the year. It also, the energy modeling software I use, REMRate, very common residential software, does some carbon estimating. And that was sort of a equitable result on a carbon basis. But yeah, it left some questions about when I'm using the electricity that I would be using, where is that coming from? So I did a solar analysis for my house, and it's not an ideal site for solar, as Google Project Sunroof can tell. If you haven't used that tool, it's a nice little feature. And it basically, because I have a lot of mature trees around it, I have a lot of good solar access for on my roof anyway. And knowing that the electric grid in Illinois is mainly nuclear with some coal and gas to supplement the 10% of renewables we have, my question was whether I would be trading my gas furnace for a coal-fired heat pump or nuclear heat pump, basically. And it really comes down to thinking about how energy flows, where energy comes from, and where it goes. So if you look at the end use, the residential slice of this pie on the far right, you can see that's what we're talking about here is residential end uses and the types of energy flows that go into that. And the number one area that we're pulling from is from electricity, right? Well, we have to realize that we're losing some electricity in the conversion process, the source energy issue that Nate was talking about earlier. So you have to kind of bounce it around to get to see what the end use is. And without the ability for solar on site, I'd have to be relying on that grid. Now, hopefully CEJA will be encouraging more and more renewable transition, and the costs, as Nate pointed out, of solar come down. But I'm kind of interested in decarbonizing now, not in 2050. And so when the opportunity came up to be a pilot site for an air to water system that offered significant potential for decarbonization, I kind of took advantage of this. So this is a gas-fired heat pump. Yes, it's natural gas combustion happening outside to drive the heat pump process. But it's running at 140% efficient compared to conventional gas systems, which top out around 97% or so at the best. And these systems provide, it's an air to water heat pump. And the nice thing about any air to water, whether it's electric or gas, you've got Chiltrix, Space Pack, a bunch of others doing electric versions, is you can run both water heating and space conditioning off of one system, right? So you don't have a heat pump water heater that's robbing BTUs that you were put out by a mini system. So kind of nice. And the other thing I really liked about this system is that it's a package system with ammonia refrigerant. Ammonia is a 0 GWP refrigerant as opposed to R410A, which is much higher. So results of this was that it did decrease some of the operating costs. It had some increase on carbon, on decarbonizing my home compared to the grid with no renewables. And lots of lessons learned here. So there were, like I said, this was a prototype system. And some things we relearned here, like condensate lines can freeze, right? So this happened again to me, and different installers. So in just different system than in the mini split. These are really plumbing jobs. When you talk about air to water heat pumps, it's a hydronic system. So that's important to know. Many HVAC contractors aren't as comfortable or familiar with that type of role as forced air systems. One of the nice things about being early is that we got to help feedback and inform the manufacturer, who is now making a more plug and play friendly system when they bring it to market, which is kind of nice. All heat pumps need to defrost when it gets moist outside and it's around freezing. And so that will cause the system to be less efficient at those conditions. Because the coils you have to get the frost off the coils for it to regain its efficiency. Maintenance is similar to other systems and did cut down gas 30% or so. So I think that's all I have. Thanks for letting me share my stories a little bit, and look forward to hearing what Alex has to say.
You're muted, Jackie.
Thanks. I was just thanking Jason and appreciating the plug for hiring. There's a lot of good work to be done. So yeah, Alex is the owner of AT Mechanical, located in Melrose Park, Illinois. Founded in 2004, the company provides piping and sheet metal design and installations in various market sectors, such as multifamily, industrial, office, process, and retail, including new and retrofit and replacement work of all HVAC component systems. AT Mechanical performs many projects as design build, as well as many as plan and specification, enjoying a robust relationship with the engineering and architectural community in Chicago. Alex graduated as a mechanical engineer from the University of Toronto in 1986 and has worked with Geo A. Kelson, F.E. Moran, V.A. Smith, and Westside Mechanical before starting AC Mechanical. So Alex will be offering the contractor perspective, which is a huge piece of making this work. Alex, are you ready?
Yes.
Awesome. Thank you.
Thank you. This is my first webinar, so I will do my best. Thank you, Jackie. I'm excited to share our mechanical contractor experience. We've done a lot of projects replacing, gas furnaces, condensing units, such that has a similar skill set as what we're doing here in replacing or adding new heat pump type systems. The heat pumpification has some interesting twists, which we're going to talk about today. I'm going to focus on heat pumpification of existing and occupied buildings, not so much new construction. We'll talk about that because I believe this is the bulk of the kind of work that is out there. That's the kind of work that we're doing. And I'm also going to focus on this because Katie has told me to focus on this.
I did. Thank you.
I'll do my best to share our experiences in some recent and ongoing projects. So everyone watching today will get a good idea of the pros and cons and the good and bad of doing the heat pumpification. And we'll touch on electrification also. Next slide. So I mentioned there's three types of heat pump systems used in retrofits. This would be in, not so much in occupied buildings, but in just in any building, new construction or gut and remodel. So that you have your split heat pumps, that's the green. You have what I call vertical VRF systems, which, are the, everyone calls things by different names. Somebody calls it a wall mount, somebody calls it a ductless split. But what I call a vertical VRF system is when you have a large heat pump on a roof that's connected with risers down to 1, 2, 3, 4, 5 floors, or it splits on a particular exposure. You don't get to pick heating or cooling. The system allows you to have heating or cooling as a polling type system. Nate kind of touched on that type of system in one of his slides. Then you have your heat recovery VRF systems, which are the most popular in new construction type systems. Again, all the devices are joined together. You put these boxes in the hallway or in little rooms, and you take advantage of, one side of the building has heat, and the other side of the building might be in cooling during shoulder seasons, that kind of thing. But what basically today, like I said, focusing on occupied buildings, we're going to talk about the best option, which is our only recommendation for occupied buildings, is the split heat pump. And that is a hyper type heat pump, which Jason touched upon. It can have a very high capacity down to, a very low temperature. So you have a heat pump on the roof, and then inside you have some type of terminal unit. We have a slide for that. And then, you either add some supplemental heating, meaning an electric coil, and then, in a multifamily situation, all the operational costs here go to the tenant. And, where I say bad and very bad, I'm not saying they're bad systems. I'm saying in an occupied building, it's very difficult to, retrofit a system like this, which require wiring and communication between all the different devices, terminal units. And then also, and Jackie touched on this too, remember the building that has no AC, and then suddenly it has cooling, that becomes an extra cost to the tenant, but it also becomes an extra operational cost. And I think Jackie did a nice job of explaining that, this is a process that we're all trying to figure out, and not necessarily about energy savings, but about, electrification or sustainability. Next slide, please, Kate. This slide shows you in an individual split type system, the type of unit that's on the roof, that would be a single zone. And I say hyperheat because that's basically what you're going to have to use in every application. So you have your single zone, a hyperheat type units, which is connected individually with line sets and power and interlocks with your vertical furnace. Now I say vertical, but those are always multi-position furnaces. They can become horizontal furnaces. The floor console you don't see too often. That's just something that looks like a little radiator along the wall. The air goes in the bottom, comes out the top. The ductless wall mount or ductless split is something you see a lot. There's 4 different versions of them, in this case from Mitsubishi. You have a ceiling cassette, which you have 4 different versions of there. You know, that is supposed to fit into the ceiling. It's typically not going to work in a residential application unless it's a ceiling mount type thing. Or that's not what you normally see. That's more for a commercial application, an office. See, it's typically like 2 foot by 2 foot, so it fits in a ceiling grid. Then you have your ceiling ducted units, which, you know, we in the industry call like a pancake unit. You just take a unit, kind of flatten it out, and that's a ducted unit. Okay, so those are your typical terminal units, but for the most part, you're going to see, you know, a single zone unit connected to one of those devices, be it a ductless split or a vertical furnace that'd be in its own room, or horizontal. Behind that, tucked behind it, is what we call a multi-zone system, and that's not like what we were talking about before with the vertical VRF or the heat recovery. Those are ones where you, for example, have 2, 3, or 4, say, ductless wall mount units connected to one unit that's outside. So you'll see that that's a more expensive job. So that's your, you know, the heat pump is what I call the thing on the roof. Terminal unit is what is inside the space. Next slide, please. So Katie asked us all to highlight things that were important. Unfortunately, every single thing on this slide is important, and I have to go over it. I know Katie's watching my time. So
I am.
factors to consider when deciding what type of heat pump system to retrofit in an existing building. Obviously, the height of the building. We're not going to get much more above a 4-story building. And sometimes you get a 3-story building in Chicago where you have kind of a garden unit. So there's your 4 stories. And whether the residents stack, okay, they typically do. And they really have to, because the way we do these jobs is, you know, that the property manager or owner is going to notify these tenants in a stack, you know, the 4th floor, the 3rd floor, the 2nd floor, and maybe the garden floor. And we have to have all the equipment on the roof with whatever roof support. It's got to be there. The electrical all needs to be pre-piped. And then we're going to come in and tear out whatever or put in brand new the furnaces or other devices. And really all that has to happen in 2 days, because remember, these are occupied units. And then, you know, these aren't in any particular order. When I say the envelope, existing condition, the outside wall insulation and ceiling, the rooftop R value that's existing, the existing quality of the glazing is a double pane, you know, the U values of the glass and the percentage of perimeter glass. Those are all going to be determinants, you know, when you do your load calc, whether this is a good application or not, okay? The other thing is the existing HVAC infrastructure in the building. What are you keeping, not keeping? We'll get to what's a good candidate building, but a lot of these buildings, as Nate stated, they are, you know, like a steam boiler, radiator type building. So they don't have any air conditioning other than window shakers. So there's some consideration there. We'll get that in a slide coming up, but the load calculation is critical. And then if you're going to be retrofitting or changing out gas furnaces to new furnaces, or you're going to be creating a mechanical room, taking up some closet space, or going horizontal to your carpentry, drywall, architectural requirements, to house the equipment and access to that equipment for maintenance. Those are critical factors. The quality of the existing roofing, can it support new equipment and systems? I mean, these, I'll show you a picture. These things get very heavy. And I would say almost most importantly is your existing electrical infrastructure. We'll touch on that in a little bit. Existing plumbing, you know, does it have condensate drainage systems? I mean, you typically wouldn't have that if you never had, if you had, for example, a gas furnace, you're not going to have a condensate drainage system unless you had humidification with that. So, you know, you gotta, these are a lot of the considerations that you need. Also, supplemental heating. I'm a big fan of supplemental heating. In new construction, I want to see it all the time because when these systems fail, you basically have no heat. So you need to have some consideration as an owner of how you're going to do that. Now, sometimes in these retrofit applications, it's very difficult to add supplemental heating, and that would be a 5 kW, 9 kW coil, that kind of thing. But we do recommend it. Another thing is the desire by the owner for more electrification, domestic hot water systems, clothes dryers, range of stoves, retail feeds, if there's any, and makeup air units. Makeup air in Chicago you need if your building is over 55 stories. So that wouldn't qualify for your typical, you know, 3-4 story walk up, which never has makeup air in Chicago. And of course, the last point is the capability of the ownership or property managers in handling the tenants and managing expectations. These are very, very intrusive operations. A lot of times when we're doing these, the family is in the building. They're in their unit. They're walking around. So we're basically there for a day or two when we're doing these tiers with the people there. So, you know, obviously you can imagine the kind of issues that can come up, but the owner and property manager needs to do a good job of selling the benefits of the heat pump retrofit to the tenants. Next slide, please, Kate. So here's, we're looking at the candidate buildings. Again, we're dealing with occupied buildings. The best candidate is a, when I say 1 to 2 story, I mean single family residence. You know, 4 story, I'm talking about multifamily. It's a building that's been renovated in the past 20 years with you know, an upgraded envelope, window and roof upgrades, as well as, you know, minimum 100 amp or 125 amp electrical panels, an existing gas furnace and ductwork with AC units on the roof. Okay, so that's a building that maybe was modified in, you know, in the 90s or the early 2000s, and it's ready for an upgrade. But you don't have the hill to climb with the envelope, you know, modifications that you need, because those have been done when the renovation was done 20 years or so ago. Okay, and the next best is something that has just an existing gas furnace but no central air. Again, you got to watch the panel size there. The good candidate is the same as the above candidates with the envelope modifications, is what I'm saying there, but with heating from steam or hot water and some space, either vertical closet or horizontal volume to house a split unit. And I caution a lot of the places that we go to, people got a lot of stuff, and there's not a lot of room to put these things. So that can be quite an uphill battle in a space that doesn't have a traditional or legacy, you know, gas furnace with duct, which means it has a room, that kind of thing. So we need to take up a room or space. When I say not good candidate, I'm not saying they're not good candidate, but you're not going to get the results that you want in a building that just doesn't have the envelope upgrades. You know, basically an old building with really no perimeter insulation or very little, you know, not good windows and not good roofing, and basically very few or little envelope. Yeah, we can give you a heat pump AC unit, but you're going to need to keep your heating, because that thing's going to work down to about 25 to 30 degrees. And from that point on, you need to turn on the hot water heating system. All right, next slide, please. Okay, so other considerations, variables in construction, execution, and pricing. Okay. The new equipment sizes. Okay, as you can see, this is a recent installation. You've got the non-roof damaging supports. You see, we put them up about 2 feet because we don't want to have any snow touching these units. You can get snow drifts up to 3 feet. So yeah, on that day, something's going to touch it. It's not like they're designed to not have any snow on them, but the good design is to get these things up off on the roof. And you can see that they are very large. So I want to put this slide up there to manage these expectations. So your units inside and on the roof get bigger with the size of the residence and the quality of the envelope. I've got some slides that'll kind of illustrate that. And a lot of these old buildings that we're talking about, in particular in Chicago, is that they have very large footprints and they have a lot of 3 or 4 bedroom apartments. Well, maybe not large footprints per se, but they have 3 or 4 bedroom apartments, but a lot larger than your traditional market rate 1 bedroom or 2 bedroom type of things. And you rarely see a 3 or 4 bedroom in new construction, but you always see a 3 or 4 bedroom apartment in affordable housing. Seasonal timing is important. Chicago and probably other cities have a heating requirement of 68 degrees from June 5th to September. I think we should have reversed that, but September 15th. Okay, no, I guess we had that right. September 15th to June 15th, you need to guarantee as a landlord that the temperature stays from 68 degrees. That is not a big window to do an install. I mean, it's a fine window, but you're not going to do all your installs. So you need to be prepared to be working in an environment that, it's 30 degrees outside, for example. So you need to plan you got to be in and out of that unit in a certain amount of time, and you need to provide electric heaters. Obviously, summer's the best time, but again, short windows. Lately, we've had fluctuating deliveries, and the pricing is just gone stupid. And that's a big problem lately that it doesn't seem to be solving itself lately. We'll talk about that in a little bit. Routing of electrical power, interlock power to the heat pump, other appliances if you choose to do electrification, and the refrigerant piping and condensate drain. It helps if there's a route, for example, a flue, to run the refrigeration piping and conduit through. A lot of times it's an old combined flue, like say 13 or 14 inches, 12 inches. We've got to get all our stuff up, because remember, all 3 or 4 units need to be done on the same day or 2 days and started, because you can't leave one unit as gas. Everything has to be done. So you got to have a crew size there that's going to make sure that everything happens. If you run into some problem, you need to fix it. And then when we talk about the roof, we talk about the future electrical needs for future solar should be considered, because that's something, if you're doing the work, you need to run a conduit from the main all the way up to the roof to get a hold of those future solar panels. Next slide, please.
Yeah, about 3 or 4 minutes, Alex.
Okay. Again, structural considerations, we talked about that. You're looking at a job that's about 1/3 finished. So there's going to be a lot more of those devices on there, probably actually twice as many, so maybe half finished. You are adding thousands of pounds of weight to the roof. Each one of those, that has 2 units on it, that's 1,000 pounds right there. So if you have 4 of them, you're looking at 4,000 pounds. Not necessarily a problem, but you need to look at your roofing quality. Again, we talked about the Bigfoot type systems that do not damage the roof. They hold the units up above, keeps units up and above future winter snow levels. And Jason, by the way, we cut off all the mechanical fittings and we braze everything. There's not even a consideration to use any kind of mechanical fittings. Your rooftop must be completely available for this equipment. And if there's a desire for future solar panels, that's something you got to draw and coordinate ahead of time. And, sorry, it doesn't look pretty up there. It's pretty to me, but, I don't think you can fit your rooftop bar up there in the future. Bottom line, roof gets very busy. Next slide, please. Here's an indoor installation that required a larger unit than the gas furnace it replaced. In this space, there was a gas furnace. We took it out. This was the size of the furnace that was determined by the load cap. Okay, I'm saying required a larger unit, but it fit just fine. Okay, it just fit. This is why the existing envelope is so important. This is one of the most important things of this presentation. Better envelope that you have in your building equals smaller units and equals a smaller electrical load. Those are the three critical components. Next slide, please. Here's another example for a 3 or 4 bedroom. Okay, you see the existing gas furnace over there. It was taking up a considerable amount of space. But when you look at the unit that replaces it, it's a very large unit. Indoor installation that required a much larger unit. I believe it had supplemental electric heating also than the gas furnace it replaced. The lesson here is fix your envelope first, electrify second. That's an important lesson. Next slide, please. We'll just go through this quick. Electrical panel sizes, electrical coils. This is going to drive the thing up. Consideration of hybrid systems, part or almost electrification, deliveries in and out of space, demolition, removal of existing equipment, electrification of common amenity spaces, dryers, dishwashers. I don't think that was the right word. Domestic hot water, electrification systems. That's typically a big problem. If you do, you'd want to keep those on gas. There's not a lot of equipment in the space. Future preventative maintenance, access, those kind of things. And noise expectations. Okay, these heat pump units are quiet, but they're not quieter than the nothing that was on the roof before. The next slide, please. Okay, so let's talk about the future, 23 years from now. So I'm going to guess that we're going to have much higher, if we compare the last 25 years to, the next 25 years or currently, I'm going to guess we're going to have much higher efficiency equipment. We might have different kind of refrigerants. We might have refrigerants that are not based upon gas. There's a lot of exciting technologies that, seem like very space age, but they're out there, and someone needs to find a way to bring them to scale. Different methods that draw less amps to perform heating, air conditioning, moving air, clothes dryer, dishwasher ranges, etc., domestic hot water. Okay, right now we're using heat pumps. Somebody can come up with some different kind of technology. I always joke somebody's going to come up with the heat pump stove. Who knows? So, and then this other one is, for my electrical buddies, partners, different methods of sizing requirements. For example, Chicago has different sizing requirements than, the international code world. So if that can help, obviously safety is first, but if that can help sizing the equipment plus less energy usage, future equipment, that will solve a lot of problems of having to jack up the electrical service in a lot of these existing buildings. And then the other thing I throw out there in my attempt to be an electrical contractor or engineer is possibly, putting retrofitting controls to existing, let's say 100 amp panels to limit the amount of connected equipment that can come on. So for example, if you're electrifying your whole space, you have an electric range, you have an electric dryer, you have an electric heat pump, domestic water heater. Well, maybe, not all of those can come. One of those can't come on of the 4, that kind of thing. Again, something I'm throwing on the table, not too much of an expert on. And then here's a note for some new construction for anyone who might be a developer out there. Plan today for future 100% electrification. We do jobs today. For example, we're doing a 200 unit. We're doing a couple of big jobs where we provide gas for a gas range. That helps the electrician It's 200 grand more for AT mechanical, but it helps the electrician because he can lower his price by 500 grand because it's a fully electric building except for the gas range. Now he has to provide 150 amp panel and size his main panels accordingly. He gets down to 125 amp panel, saves a whole bunch of money. You got a gas range. All I'm saying is size the conduit for that gas range for, you know, a future more efficient range somehow. But don't put a 3/4 conduit when you know you're going to have to pull 2 wires in 25 years, okay? Because you're going to do that later, it's going to cost you a fortune in 2045. I think that's the end of my presentation. Yes, it is. Thank you.
Thank you, Alex. There are a lot of questions and only 14 minutes left. So I'm going to jump in to some of the questions. Alex, I think I'll start with you. We just heard all of the extensive details on this, and you know, you're talking about designing for the future. There's a couple questions specifically on maintenance and how long, what the durability of the systems are. So could you speak just for a minute about what is ongoing maintenance like and how long do these systems last?
Well, a typical heat pump, you know, I mean, we install, we're a Diamond Star with Mitsubishi certified installer. So when we do something, you get additional warranties, including labor and parts warranties. But we also install LG, Daikin, you name it. So we're not beholden to anyone in particular. But, you know, the thing that's for a contractor somewhat frustrating, but not necessarily for the maintainer, is they don't really want you messing with their equipment. They want you to basically clean the equipment, change the filter inside. The equipment is very robust, and it's not really designed to be that serviced. If you look at, for example, all these systems come from Japan, and then everyone has copied them. When you don't go to fix a wall mount or a ceiling cassette in an office, because they use it everywhere. You just go in, suck the gas out of the system, pull the offending unit out, and put a new one in. That's basically how you're doing maintenance with these equipment. But I find them to be very, very robust. If you wanted me to throw a dart on the wall, I'm saying that if you maintain these systems, you know, and that just means having someone clean the outside coils, making sure, you know, that it's a proper installation, you know, that you don't use the mechanical fittings, never, you know, that it's got a good location where it's in, and that, you know, the coils aren't clogged up with dust and everything, and not even the filter. Like, even people forget, like on the wall mount, it's got this little plastic filter. Just take it, run it into the laundry, and just because I'll tell you what, I've forgotten it, and then you just all this drips come down your wall. The unit feels kind of, you know, damp, like it doesn't condition as well because you're blocking the air. It means you get colder air. You're getting a lot more, you know, condensation because you got a colder coil, servicing less air, those kind of things. So it's just basic maintenance. Keep the things clean, check the electrical contacts, because they're not really going to let you into the world. Mitsubishi doesn't want you replacing. I've done it. I've replaced compressors and stuff like that. They don't want you really touching it. You got a problem? Take the old one out, put a new one in, okay? And just make sure nothing burned out, and your typical refrigeration type of things, filters, all that kind of stuff. So, you know, that's the answer. Gas out of system, 15 to 20 years.
Yeah, and I think what you're saying, and people should remember, is that this is the same for any equipment. You have a gas furnace, the performance is going to be longer when you're taking care of it. And so that's true for heat pumps as well. Nate, we're going to jump to you and talk about how you address indoor air quality, and generally, you know, what other benefits like indoor air quality do you think are not being discussed as much?
Yeah, so I mean, on all our new builds, you know, we're really going with a direct duct direct ducted supply, energy recovery. We really want to try to get away from a pressurized corridor situation. In some of the rehabs, it's sort of, our hands are a little bit tied with some of the budgets that we have, but we know that, we want to get that fresh air direct in. If we can't do that, we have ducted bathroom exhaust that's running either continuously at a low CFM, or it's and with a boost during occupancy or high humidity. So, that's what we try to target, but sometimes we are falling short, and we have to do the best we can with sort of the existing building we've taken on.
Oh, muted Jackie.
And what are some of the other benefits, like indoor air quality, that you think are not being discussed as much related to heat pumps?
Oh, indoor air quality as related to heat pumps, and not being discussed as much.
As a benefit of the technology.
Oh, well, I mean, I don't know about indoor air quality per se. I think it's obviously important. It may be integrated to equipment that's providing fresh air. It may be decoupled from that equipment. So the strategies I mentioned, I think that's the ideal circumstance. But heat pumps and indoor air quality, I think it ties back to just proper maintenance, proper cleaning, making sure the filters are maintained properly. So that's my response there.
Thank you. Yeah, we're definitely seeing in the full electrification package, removing combustion appliances is a benefit. Jason, can you talk a little bit about, well, you're addicted to heat pumps. I hear you have plans for a fourth one. How are you making decisions on this?
Yeah, that's a good point. A good one. Didn't have time to share it, but it sort of speaks to what Nate was talking about briefly. The idea of a hybrid system where you have a heat pump doing a majority of the heating, shifting a lot of the space heating to the heat pump, but maintaining a furnace for backup heat or peak conditions. And what I really like about this is there are control strategies being developed that can choose which system to operate based on operating costs, like especially with pairing it with time of use rates on the electric side, or looking at real-time emissions from the electric grid and seeing, does it make more carbon sense to run the furnace versus using a gas peaker plant that might be filling the load to meet grid capacity demands. So some really interesting potential technology out there. In fact, I think Mitsubishi has a system coming to market in the next month or two that will be doing that. So I'm anxiously awaiting that arrival. So thank you.
Yeah, and I think that is an example of meeting people where they are, as well as just designing for a future that is for electrification, but recognizing that there are options in the technologies. I know you have a lot of lessons learned across your experiences. Will these be written up somewhere for everyone's benefit?
Yeah, specifically with air to water heat pumps, I really think that this is an important technology for addressing especially multifamily hydronic based systems. And so whether it's a single family like I did or in a multifamily application, there are a lot of installation tips and tricks. And I actually partnered with a couple of people to write a paper at the ACEEE summer study that will be published in a couple of months, talking about best practices and lessons learned of how to put air to water heat pump systems into place.
Awesome. Well, stay tuned for that. So I just want to give all the panelists one more minute to speak to what they feel like people can do first. You all have shared a lot of detail. I'm glad that there's a recording, because I know I'll go back and take a deeper look at the slides where everyone had bullet point lists and multiple slides of lessons learned. And we're really just getting started, I think, in the cold climate, at least affordable housing multifamily space. So lots more to learn. But yeah, if each of you could just share what you think people could do next, or first rather, what people could do first when considering all of the lessons, like what's the thing that jumps out that you want to leave folks with? Jason, you want to start?
Yeah, I'm going to take a page from Alex's notes book here. And, heat pumps is the topic that brought everybody here today, and great attendance. But it really starts with buttoning up the envelope and reducing demand. You'll get a significant more quicker payback and to deliver the comfort that you expect these systems to perform. Because if you misapply them, then things won't work well. And that, we want to make sure that this is all going in the right direction. So yeah, envelope first, heat pump second is my suggestion.
It's the gift that keeps on giving. You don't even bother calling us until you've done that first, really. Because once you do it, it's there forever.
Very important to look at this comprehensively. It's really pivotal to look at the whole system in order to make this work. Nate, what about you? Last words?
Yeah, no, I was just gonna say, like, don't forget about the simple stuff. I know everyone is sort of like beating a dead horse to a degree, but like all that stuff really matters when you're talking about adding more electrical equipment to your building. So where you're reducing, that's freeing up space so that you can not have to upgrade your service to your building, which is going to limit you in a number of ways. So don't take those small things lightly. And obviously, the enclosure is super important, and drive down that heating load and that cooling load.
Great. Well, I think I can speak for everyone here that we're all committed to sharing ongoing lessons learned for the greater good and working together on climate change solutions. I know at Elevate, we're excited to keep trying to connect people to the resources and then bring those people back to talk about those experiences. Katie, do you want to go ahead and close us out and wrap up for our last few minutes?
Yes, thanks, Jackie. First, I want to thank you for being a wonderful moderator and stepping in and moderating this panel and adding all of your great commentary. It's really, really wonderful conversation. And I think a couple of people said in the chat, this time just flew by. We all wanted to nerd out about heat pumps today, and I think we all got that. So thank you all for helping us achieve that today. Still 170 people tuned in an hour and a half later. So congrats to everyone for being here. I really want to thank Alex on his first webinar experience. Thank you for sharing it with Illinois Green. You killed it. Appreciate it. Thank you so much to Nate and to Jason for speaking as well and sharing your experiences. And thank you to Mohammed and the Programs Committee volunteers for putting this program together. I think there were some really great lessons learned. I think you guys all could have probably talked about this for 8 hours. So we'll have to figure out what the next sessions are that follow this, that we can dig in a little bit deeper. So we are going to take all the questions from the chat, the questions from the Q&A. We'll put together a great document, hopefully, to share out if you missed some of those answers. We'll send a follow-up email with that Q&A, with the recording from today's session, and also a PDF of the slide decks. If you have any ideas or thoughts about what a next session on this topic could be like, please reply to that email, send it our way, and we'll see what we can do. But thank you again all so much for presenting today and sharing your experiences. We really, really appreciate it. And thank you for all the attendees for being here. Have a great afternoon.
Thank you. Bye.